The broadcast is now starting. All attendees are in listen-only mode.
Greetings and welcome to today's webinar. I'm Mike Micheletti and I'm a product manager here for the USB test equipment we make at Teledyne LeCroy. Thanks for joining us. I know it's hard to find time to attend training classes. Today we're going to be covering USB Type-C testing for compliance and interoperability. We're going to be covering a lot of material pretty quickly. But don't worry, you can always replay this recording on demand after the presentation. I do see some familiar names on the roster here from past PlugFest, so thanks for logging in. We actually host several test suites at the USB workshops that feature our USB test platform, the Voyager M310C. A lot of you probably have this system in your labs already. It supports link layer, hub, PD, and now Type-C compliance testing. One of the things I notice at these events is that a lot of attendees are not that familiar with the official test procedures. So I like to hold these webinars to give them an inside look at how the testing is done. So you guys will be way ahead of the game. Of course, I will send out a link with the slides and the video in the next day or so, so look for that. Today's agenda will include a quick overview of Type-C operation and the compliance requirements, and then we'll get right into the test implementations. As I mentioned, a lot of you probably have our Voyager platform. One of the reasons that people don't go under the hood on the individual tests very often is that it's very turnkey, where you attach a cable and hit go, and the software does all the verification, it does all the work. And that kind of hides the complexity. So this is really one of the most demanding test specs we've ever covered because it combines a lot of electrical measurements with protocol layer events, both USB and PD, a lot of precise timing. You know, any hiccup could cause a reset and the test has to restart. So it's very challenging. The only way to really learn it, though, is by looking at traces. So we do have our giveaway today, one of our Mercury Type-C analyzers. Everyone logged in is automatically entered, so stick with us. Yeah, this could be your lucky day. We're going to get right into a lot of technical detail. Having some background, though, on PD protocol is helpful. So a quick plug. If you're new to Type-C and PD, you may want to view some of our USB webinars from last year. Just search for webinars on the Teledyne LeCroy website. Either way, I'm sure there will be questions, so please type in your questions using the question chat box. I'll try to address those at the end of the presentation. If you're on this webinar, you're probably familiar with the features that the Type-C connector is going to provide. I won't spend a lot of time on this, but it's the plug orientation and the default power roles that are the key focus of the functional test spec that we support. We want to make sure you can connect to all the different device types out there. Any problems in this part of the design could really result in the device being unusable, right? So the alternate and the accessory modes are another focus area for testing because, well, this functionality is all new and it depends on CC electrical states. I got to tell you, I'm surprised by just really the scope of what we're actually testing here in Type-C. Because, you know, if you lived in a world with just sources and sinks, the test set would be relatively small, but Type-C introduces new device types and some new device behaviors, functionality designed to give developers more flexibility in developing end products. So we're going to verify that the DUT follows the proper protocol when connecting to another DRP. Does he properly connect with audio accessories? Does he follow the proper procedure when connecting to a tri-sync and a tri-source device? There's tests to make sure he recognizes debug accessories and VCONN powered accessories. Yeah, I know that the chip guys out there say we covered all that in simulation, but you know, to get certified, they still want to see this over a cable. And one of the key challenges with passing compliance is really just figuring out what needs to be tested, because there's a range of functionality that's optional. with Type-C. Most of the new devices showing up at the Plug Fest today are using the Type-C connector. So this is one of the busiest test suites. If PD is supported, you have to go through the PD suites. And of course, if the device supports data, it has to pass all the mainstream USB compliance tests. So say you walk in the door with a Type-C host or a device. What are the high-level requirements for compliance? Well, if your device supports data, it's going to be subject to the SuperSpeed electrical spec, which includes both transmitter and receiver. The USB 2 electricals are also tested. There's a rigorous cable and connector test spec. This is very specialized. It's only offered through authorized test houses, so that spec is really down at the individual component level, the mechanical aspects of the connector. If it's an end product and has a cable plug, there's a smaller subset of tests in this spec that they have to pass. Now, if devices source power over Type-C, it will have to pass the source power tests. This is also known as the Quadramax test suite, which is really, it's much more focused on PD-enabled power sources, but every Type-C host or hub will also have to pass these tests, even if they don't support PD. They also enhanced the USB interop test spec with specific tests for Type-C. So that's where they do the gold tree testing, which is mostly USB functionality, right? You got to enumerate, show that you work with a known good host. They also test both orientations of the cable here. And then the newest spec, the Type-C functional, which is the main focus of our webinar. This really covers all the basic operating modes of a Type-C device. There's lots of electrical measurements in these tests, plus protocol stuff, timing. There is some overlap with PD compliance. Both specs do alt mode entry and role swaps. But as we dive into this, you'll see that the Type-C testing is far more comprehensive when it comes to just your logical connect states. And I put the official USB-IF test matrix in here just for completeness. It shows the device type on the left and then the test spec you'll have to pass at the top. And what you see here is that pretty much everything except cables has to go through Type-C testing if you want to pass compliance. Of course, if it's also PD enabled, you have to go through the PD suite, and then USB. That means several additional test suites. So a lot of testing. But finally, 2.5 years after introducing Type-C, most of these test procedures are now nearly finalized. PD 3.0 is still getting developed, but certifications for Type-C end products is available at the USB Pill Lab right now, and should also be available at the workshops very soon. So as I mentioned, the Type-C functional tests are supported by the Voyager, the M310C, which has the native Type-C ports. You would just connect directly to the DUT. Setup is basically the same for a source or a sink. And the M310C is considered approved for doing this compliance verification testing. It's basically considered a CVS. So when I refer to CVS, that's the Voyager. It's capable of emulating all these USB and Type-C devices. So it's used during the workshops, and all the test examples we're actually going to look at now are generated by this system. So a lot of the functionality in Type-C is optional. Whether you need to pass some tests depends on whether you support certain features, things like USB data, alternate modes, sourcing VCONN. All of these add additional assertions to a given test. With PD, we had a similar challenge in that to test a device, we needed to know what it supports. So the compliance group created that standard format you probably all know. It's called the VIF, which it's just a text file that you fill out, and it becomes a spec sheet for the device itself. It's used by the USB-IF to track capabilities of a device coming in for certification. And then we also use it for testing. So just to walk through this so we're all clear, you go into the Teledyne LeCroy compliance test software, which you see here. Before you run any tests, you use the VIF button. It brings up a dialog where you choose Open File. You select the VIF for the device you want to test, and it'll load into this window with all the fields all labeled. Many of these are for PD devices, but some of these fields were actually added just for Type C testing. If you specify it's a source, then we'll run the appropriate source tests. If you specify DRP, then we'll pick all the appropriate DRP tests. And if the VIF indicates it supports USB data, we'll automatically run those tests that require a USB data link. So we have to check all those steps as well. So the VIF is critical. Make sure you pay very good attention to entering this information. Okay, to get us started, I'll give you a 2-minute course on Type C connection basics. Most of you, again, I apologize, most of you probably already know this, but this will be brief. The configuration channel plays a huge role in the basic functionality of Type C devices. And it all starts with detection of something getting plugged in. That's the CC channel's job. It also decides the initial roles, source or sink. It defines the default voltages for VBus and who's going to supply VCONN. And while you're at it, he needs to do all this upside down and right side up. And then finally, all the exciting alt mode stuff is done over CC. So there's a lot to test. You can't really understand Type C without looking at the pinout. And the key to understanding how they're doing this Type C configuration stuff is to really be aware that all the intelligence is in the receptacle. When you're looking inside a receptacle and a plug, these pinouts look similar, but there's a huge difference. Only the receptacle side has the fully redundant set of pins. You know, the cable is not symmetrical. Most of the connections are there, but the extra D+, D- is not connected. The A5 and B5, or actually the A5 on the cable side will always be CC, and B5 will always be VCONN. So it's the receptacle's job to figure out how the cable came in and adjust its pinout appropriately. Okay. Easiest way to explain this is with a picture. This illustrates really the simplest case, a pure source connecting to a pure sink device. The left side is the source and the right side is the sink. And for simplicity, I'm just showing the CC connections. So both receptacles are monitoring the CC1 and the CC2 lines continuously. Once the cable is connected, each receptacle will look at resistance levels on CC. The source attaches a couple of pull-up resistors known as RP, and the sink shows a pull-down resistor, or RD. So on his side, he takes both CC pins to ground. They only see this termination on the one CC line that's connected. So they know this is the line they're going to use to do PD communication. So that means the receptacle needs to use the top row pins in his receptacle connector to route the other signals. You flip the cable over and they'll see the same termination, RP, RD, only on their CC2 pin this time. So they need to use the lower pins for the other connections. If there's a twist in the cable, it doesn't matter because each receptacle needs to be smart enough to figure out which pins to use independently based on the resistance he sees on CC. So behind the receptacle, the signals are typically going to go through a mux to route the other wires to the right pins. There are also some muxless designs out there as well, but they all have to go through this same testing. So CC is always on the A5 wire. B5 is a no connect unless there's any electronics in the cable. E-mark cables will alter termination on that CC2 wire in the cable, right? They have a very low voltage resistor called RA. So when a source sees RA, that tells him that I'm an E-marked cable and I need 5 volts on VCONN. If you want me to answer any cable messages, I need a little power. So that initial source is supposed to supply VCONN. It's for the cable though, and it doesn't pass through to the far end. So just a few more words on VCONN. It's part of the Type C spec. It's also covered in PD, so you may have to look at two specs to understand it. In addition to powering eMark cables, there's also something called a VCONN-powered accessory, which is usually some kind of lightweight, simple device, like a display port adapter is one example of a VCONN accessory. So again, the default source sees RA and is supposed to source a small amount of power, like 75 milliwatts. It's basically a poor man's V-bus for non-USB applications. But when it comes to compliance, supporting VCONN is actually optional for Type C. It's not required that you source VCONN, but most PD chipsets do. So we do have some tests for VCONN in the Type C side. So small feature, but still important, and it needs to be tested, primarily to make sure it's getting turned on and off as required. We're talking about a range of 3 to 5.5 volts, so voltage measurements are a key part of Type C compliance. We're constantly monitoring power on CC1 and CC2, but again, VCONN voltage is on CC2, and remember that CC2 doesn't pass all the way through the cables, so it doesn't make it to the analyzer. So here is where we needed to create a special cable that connects CC2 all the way through to, on the cable side. So VCONN voltage will make it to the tester. There are, probably a dozen tests where we need to verify that VCONN is getting sourced at the correct voltages and within the correct timing windows. We have that ability to continuously measure voltage on CC with the tester, which you can see here graphically in the power tracker window. CC1, again, has to go all the way through because it's used to send PD messages to the far end. This is a PD message getting sent, so you can see those on CC1, always on CC1 when the analyzer is in the line. But there's no way the analyzer can see what's happening on CC2 unless you have that special cable. It never makes it to the analyzer front end. So if you switch to the VCONN pass-through, now we can see exactly when VCONN is supplied at the right voltages. All these measurements are used extensively in Type C compliance. So that cable is specifically for compliance. You probably want to avoid using it like a normal cable. You could have unpredictable results, but in a test environment, it does have uses. You could use it in the analyzer mode where the Voyager is passively just recording traffic between real devices. So here you could also see what's happening with VCONN on the analyzer, just to be sure that you get that pass-through on the correct side. The cable needs to be on the side where the source is sourcing VCONN. One more tip, if you're testing a device that needs VCONN, like a VCONN accessory, be sure to go into the analyzer, set up and check that we have turned on VCONN, the VCONN on option on that analyzer point. So this way the Voyager will make sure that VCONN is supplied to any devices on the other side of the analyzer. That's a high-level look at cable detection. Pretty simple if you have a basic sync-only device, but you'll see it gets more complicated as we look at some of these individual tests. The first tests we run in Type C compliance are considered safety tests, and you need to pass these before they'll even let you into the interop suite. First, a quick crash course in reading these Type C traces. This can be a little overwhelming when you first get started looking at Type C, but you'll need to rely heavily on these events when doing debug. So it's worth focusing on for a second. So we're always monitoring CC, and we'll put these events in the trace anytime we see a valid transition from either side, the tester or the DUT. So we can detect these voltages when they change, like this on CC1. The dark green here indicates the electrical's changed from the prior state. The lighter green, like this, is used to indicate we see RP, but it's not officially changed yet, so we're using timers to decide when these states should actually change after waiting that required time interval, we insert these labels into the trace, which identify anytime there's a confirmed state change. And because the connected state is pretty important, we show connected anytime two link partners are in attached wait, and then again once VBus is sourced. So that's the real connected state. All this information is derived, right, from the actual electrical levels that we see on CC. So this is crucial if you're trying to test compliance, to be able to capture these events. Okay, the very first test that is supposed to be run in Type C is the TD411, which is supposed to confirm that a device does no damage when it's in the unconnected state, meaning a dangling cable should never drive voltage over VBus. Obviously, that would not be good, so we test that. We connect to a DUT with a cable, but the tester doesn't present any terms on CC, so we're just sitting there. We can see that the CC states are open. We look at what's happening on VBus. Nominally, we could see some voltage from the far end, up to 800 millivolts, and still pass. We check the SuperSpeed pairs and the D+, D-. We want to make sure they're not exposing SuperSpeed terms, so no VBus, no terms. Now, if the DUT is source capable, the tester takes the unattached source roll. So we should see RP terminations on the tester side. Here we're attaching a source to a source, and we want to make sure nothing bad happens. We wait 750 milliseconds and verify the PUT doesn't source VBus. We're also going to check VCONN, so again, no VCONN, no VBus. Then, if the DUT is a receptacle, we try to trick it again by applying RA to CC2 only. So that's not a valid CC configuration because CC1 is open. So we're halfway to emulating a marked cable or maybe an audio accessory. Audio accessory, you want to see RA on both pins, but here we're just going to check VCONN again, make sure that the source isn't jumping the gun, right? To make sure he isn't applying power to VCONN. He should just remain in that unattached state. Finally, the last stage is designed to emulate attachment of a legacy type A to C cable. Okay, so this is for DUTs that have a type C receptacle, like a laptop. And here we want the tester to apply 53.2 kiloohms resistance from VBus to CC. So we're spoofing the DUT to believe he's attached to a type A cable. He's really not. We want to make sure that the type C receptacle never applies VBus in this scenario. So pretty unlikely, but we test it anyway. So the biggest chunk of testing in Type C has to do with establishing connections, which means can you correctly detect all the different types of devices, and then we make sure you can connect with them. We'll start by looking at really one of the simplest tests. In TD4.3.1, we make sure a pure sync can connect to a source. We're testing a sync here, and the Voyager system is going to emulate a Type C source. So to start, the DUT as a sync would be showing RD as soon as he's connected to the tester. The DUT is considered to be in this unattached sync state right here. The tester will be in the logical open state. We basically do a Type C reset between each test to start from a known good state. So when the tester does come back, he always comes in second, right? He's always showing up midway through the trace. It presents RP, which we show here as in basically he's moving from disabled to unattached source. As soon as the DUT detects RP from the tester, he's actually entered the attached wait state. He needs to stay in this state for CCD bounce, which is a range. He needs to wait a minimum of 100 milliseconds, but then within 200, he needs to transition to the attached sync state. This CCD bounce is observed on both sides, and it basically just provides a settling time to make sure that it's not some other event from the far end that just looks like RP. Remember that in PD, the CC lines are used for packet transmission, and these packets can look like voltage changes to the CC circuitry. So a device could be sending a PD message, and it could just look like he's disconnecting. So 100 milliseconds CC to bounce time. Again, the sync is not supposed to move to the attached state until he waits, that period, and then detects VBus. So at this point, the tester will verify that the DUT actually syncs current over VBus. If he supports PD, he needs to negotiate a PD contract, so we need to see that PS ready. And then he needs to link up a USB data connection. And that's if he supports data. So we'll check all that, and he also needs to stay in this state for at least 500 milliseconds without dropping RD. Continually showing that RD is critical because sources use RD to figure out if a device is still attached. And then on the other side, how does a sync detect when something disconnects? He'll use VBus to decide when the host goes away. So there's also a source version of this test where we check all the equivalent states for a source, right? Including, does he properly source VBus, and then removing VBus on disconnect. Okay, so back to our sync test. The tester will remove VBus, which should cause the logical state of the device to return to this unattached sync state. He has to do that within tVBus off. And the logical data link should also drop, of course. So this is really one of the simplest connection tests. Depending on your device type and the features, there may be a few other assertions that are checked. But these are the main steps. Pretty simple. One thing worth mentioning, specific to testing source DUTs, the compliance group had to actually create a couple of timing parameters to make testing possible, meaning that these are not part of the base spec. They're only in the compliance spec. And this one has to do with the transition out of the attached source state, which, according to the base spec, is supposed to be immediate. But some device OEMs that have source functionality, they lobbied for a more generous timing window during testing here. So we're talking about a DUT. That's a source. It's in the connected state. It's showing RP. Now RD is no longer detected. The source is supposed to go to unattached immediately. But how long does he have? Or really, what value should the tester use when we're checking this to make sure that the source has gone to unattached? The background here is that there's some concern that there are devices out there that implement power saving features, and these actually could cause a false detection of the device going away, of RD going away, right? Also, PD may be implemented on some products, and it could be retrying a message. So if you're retrying a message, you can't do far-end detection. So bottom line, we needed to add some slop for sources, and we came up with tDetach of 20 milliseconds. So sources will have up to 20 milliseconds to get back to that unattached source state. So when you're testing with type C, voltage levels on CC are pretty critical because they define all the logical states, but there's more. This table comes from the spec, and it shows the voltage levels that allow a source to actually advertise that he can provide higher default current over VBus. This is something new in type C since these devices are monitoring CC anyway. They decided to use the pull-up voltage level on RP to signal that he can provide higher VBus current. So this is what the source is capable of providing initially. He could always renegotiate with PD later, but it's higher. In legacy USB, voltage over USB over VBus was 900 milliamps for USB 3, and now with type C devices, you can source up to 3 amps by default. So for example, a source, an RP, right after power on, he can alter his resistance values. He'll use a 10 kilo ohm at 5 volt resistor, and that means he can provide the full 3 amps over VBus. So the spec defines a range, and if we see voltages in this range, that means he can provide the 3 amp current. A source could also advertise 1.5 amp or the legacy default current. And we're actually going to test this. We're going to check this in the TD 4.92, which is for sources and DRPs that can act as a source. So vendors need to report the amount of current they advertise. Here we have a source. It's showing RP. Its VIF indicates 3 amp current. Again, we're using Power Tracker here to verify these steps. The tester comes in showing RD. We're supposed to wait for a valid connection, which occurs, once VBus is applied. We want to see CC voltage settle in one of these ranges. The tester measures 1.77 volts, and that means it'll support the 3 amp current. In the next stage of this test, we make sure he maintains a valid range after negotiating a PD contract. So this trace is actually from a different device, so we're testing a different device here. You can see this one advertises USB default voltages. So legacy VBus. It's in the valid range around 450 millivolts. Okay, so that's CC voltage, right? Not VBus, CC. Now the tester starts responding now to PD communication. We negotiate a PD contract. Then we verify that the VRD is still in a legal range, which now has to change to either 1.5 or 3 amp. So there's a obscure rule here that they don't want devices that transmit PD messages from using legacy VBus levels. Somehow these lower voltage levels on CC can actually affect PD traffic, I guess. I'm not even sure why, but this device needs to alter his resistance levels after the PS ready to pass this test. Okay, DRPs, one of the more critical areas for testing because they're more complicated and they'll be quite common, really. So even if you're not making a DRP, you'll need to know about DRPs because we're going to make sure you can connect to these during compliance. DRP, or dual role power, means a device can act as either a source or a sink. Typically a laptop or a tablet will be a DRP because it needs to sink power to charge its battery, and it also needs to source power for peripherals. And determining which role it'll have at connect time is where DRP protocol comes in. Should I wake up as a source or a sink? Like all these Type-C modes, this needs to be done in real time at initial connection. This table shows the key timing values that we use during compliance to make sure DRPs behave correctly. Rather than read through these, I think it's much easier if we look at a diagram. So figure 439, this is right out of the spec, and it shows all the key parameters. Most of you know that DRPs are supposed to toggle between advertising RP with a pull up resistor and RD with a pull down on CC1. It's easy to see this behavior in the Power Tracker. Now, tDRP is the round trip time the device will spend toggling between source and sink. It's a range between 50 and 100 milliseconds. DC source.DRP is the proportion of that time that it'll expose source RP. So they created this formula because they wanted it to be pseudo-random, right? So it would be valid for a DRP to spend between 15 and 70 milliseconds advertising RP, and then it pulls down to RD voltages in case the other side wants to be the source. Here's an example of what a typical DRP does. Advertising RP at 48 millisecond intervals. By design, there's a lot of variability in this timing. The obvious reason is that you want to avoid connecting two DRPs together and have them toggle at the exact same instant. That would, create a deadlock type of condition. So when we're looking at DRP testing, okay, so if a DRP is powered on and it's waiting for a connection, he's effectively toggling between the unattached source and the unattached sink states. We're going to check this. We're going to check how long he stays in these states to make sure it's within that 15 to 70 millisecond range. So that interval is, well, it's really up to the DRP what he wants to use, but there's a bunch of tests where the CVS system will emulate DRP behavior. And because they wanted to make sure the DUT can tolerate different DC source DRP times, they're going to alter those intervals as shown. So anytime the tester needs to act like a DRP, we're actually going to repeat the test 9 times with 9 different timing windows on the DRP side. So no matter, again, what type of device you have, you will have to successfully connect to a DRP that's running with all these different timings. This table also right out of the Type-C base spec, and these parameters are used repeatedly in Type-C. The CC bounce, which I already mentioned, this is specifically to allow the CC to settle, namely because Type-C devices can't empirically determine what the other side is doing, right? There's no real handshake. It might be about to toggle to RP terminations, so it's really a guard band, or maybe more of an interim state. They call it attach wait, and it's there to make sure it's a valid attached state before you consider the link connected. And the range, again, 100 to 200 milliseconds. Then the PD bounce is specific to detecting a detached state. So this is really kind of the opposite of CC bounce. You're currently connected in the attached state. Then one side may decide it needs to send a message over CC, like a PD message. And these could look like a drop in voltage to the link partner, right? So he goes ahead and detaches falsely, and that'd be a problem. So PD bounce was defined again just for this reason. It's a range, 10 to 20 milliseconds. So these come into play anytime the DUT is supposed to connect or disconnect as a DRP. Okay, this is an illustration of the test 453, where we're testing that a DRP will connect to a source as a sink. Okay, so here the DUT is a DRP, the tester is a source, so we're going to be showing RP on CC1. We need to see RD from the DUT within max DC source.DRP times max tDRP. What's the max amount of time a DRP can show RP? It's 70% of tDRP time, or 70 milliseconds. Okay, so once we see RD, we check that he maintains RD without switching back to RP for 100 milliseconds. So that's actually your CC bounce. Then the link is considered to be connected. You'll see this event in the trace indicating the default voltage. Then we go to the open state for 100 milliseconds. When the tester goes disabled, the DUT will float back to the pulled up state. You'll see RD initially, but he will eventually need to go back to that RP state within 100 milliseconds. He'll need to toggle, right? So as a DRP, he should go back to toggling to that unattached source, unattached sink. We wait 750 milliseconds. Then the tester comes back showing RP, and basically we do the whole thing again. We're showing S source terms. We verify he gets back to unattached sink, again within 70 milliseconds of the tester enabling RP. Then we should see the connected state. So we go all the way through twice just to make sure he can reconnect. If the DUT supports data, he has to actually bring up a data link here. We make sure he gets through the LMP exchange if he's a SuperSpeed device. We then drop the link by removing VBus. We make sure he transitions to the unattached sink state. He has 20 milliseconds to do that. We also check that he stops drawing any current over VBus. So for a DRP, there's a lot of checks, and I actually even skipped over a few. So lots of stuff to test, and there actually are a lot of tests to be concerned with here, because actually there are 14 different connection tests for DRPs, just to make sure he can connect in both the sink and the source roles when he runs into all these other different Type-C devices. So in order to provide sort of a better user experience, device OEMs wanted a way to cut down on the unnecessary role swaps, so they came up with this tri-source, tri-sync DRP concept. The idea is pretty simple. Anytime you're connecting two DRPs, either one could end up as the source, right? That's how it's designed, with the toggling being somewhat random. But there are usage cases where you might strongly prefer to have a DRP come up as in a certain role when connecting to another DRP. Say you have a laptop, which is a DRP, right? Most tablets and laptops are DRPs. You attach a smartphone, there's very few scenarios where you would want that laptop to come up as a sync here. The laptop should be the source, so he can provide VBus to the phone. If these guys were sort of generic DRPs, the laptop would come up as the default sync half the time. Then we'd have to do a PR swap for him to become the real source. So with this tri-source mode, basically the laptop gets one last chance to force a role swap by rejecting the sync role, and this can only be done once at the initial connection stage. Here I think it helps to kind of use a picture, a power tracker image to illustrate. Think of this as sort of a 10,000 foot view of the CC link. First of all, let's look at a normal DRP. Okay, this is normal DRP, nothing connected, so he's toggling away. Now another DRP comes in and takes the source role. Here's another user tip. By zooming in like this, you can see exactly where the pull-up from the other side connects. The scope jockeys out there probably already know this, but the power tracker shows an average voltage, as seen from the analyzer. Okay, so after that second link partner is connected, what we're actually seeing on CC1 is a blend of the RP and the RD voltages. So it kind of settles in the middle, right? That may not be obvious to everyone. So this is what a normal DRP looks like. Now we look at a tri-source connecting to a pure source. Our tri-source DUT is toggling RD, RP. Then the CVS shows up and applies RP. The pull-up drives the voltage higher, so it looks a little higher there. Now the tri-source is seeing RP. He should still flip to that sync attach wait state, but then he's supposed to try one last time to land on that source role, so he goes back to a pull-up state. This is considered the tri-source state. Basically, he's testing to see if maybe he's connected to a DRP that he could trick into going back to that sync role. In this example, we're emulating a source, okay? So we want to see that he properly yields that source role, okay, when attaching to a power brick, right? Because remember, in Type C, devices don't know what they're connecting to. Could be a source or a sync or a DRP. So you can see these timing windows. We'll walk through one of our basic tri-source DRP tests, the TD 4.61, and we're using the state diagrams from the spec here, where we verify that our laptop obeys these tri-source behaviors. The DUT is on the right, okay, and he's a tri-source DRP, so he's still supposed to toggle between these unattached states, but he's a special DRP, a tri-source DRP. So the tester is going to act like a pure source in this test. He transitions to unattached source state, so he's showing RP. The DUT will eventually land on RD. He sees RP on CC1, so he should detect that he's attached to a link partner. Likewise, the tester should see RD. So both sides see termination from the far end, and they go to this attach wait. What do we do there? We have to wait CCD bounce. 100 milliseconds min, 200 milliseconds max. So as long as each side sees RD and RP for CCD bounce, they would move to the attached state. So the tester does, as a source, he transitions to attached source, right? He's still showing RP. So that's what a real source would do. But the DUT, his firmware tells him to wait for VBus and then transition to this new tri-source state. Here he's supposed to show RP terminations. We're going to verify that he actually makes that transition. How do we do that? Really, the only thing we can do, is look at his source terms, make sure he's showing RP. The tester was in the attached source state briefly, but now seeing RP, he transitions back to unattached source, okay, because, by rule, he's a source. He can't attach to another source. He needs to go back to that unattached source state. And then what? This is really the DUT's one-time shot right here to land on that default source role. Okay, after waiting tDRP try, so that's a bigger window, 150 milliseconds, he fails. Okay, he never sees RD from the tester. So he has to go back to showing RD himself, which is the try-wait sync state. It's basically identical to the attach wait state, but for some reason they call it the try-wait sync. And this is what we want to see. So the tester verifies he's showing our RD right here. And the tester itself goes back to the attach wait source while the DUT is still in the try-wait sync. Looks like a normal sync source connect at this point. They wait CCD bounce, then they both go to the attached state. We're going to source VBus, then verify that the DUT is in that attached sync state. We're supposed to wait at least until VBus reaches VSafe 5 before checking it that he's in this attached state. So, so there's two real checks going on there. Now, if the DUT supports PD, they're supposed to negotiate a PD contract next. And if it supports data, we would need to bring up a data link, just like we do in a lot of these tests. Another thing they do, they make us send discover ID commands for 200 milliseconds. We want to make sure he responds with good CRC, and this is done just to make sure nothing has gone wrong with the logical CC communication. So again, we verify both USB and PD links. After 500 milliseconds, the tester goes to disabled. And we should see the DUT go back to unattached sync, and the test is over. So there's a lot of steps, and it's one of the more complicated tests. This would be a basic connect for a tri-source to a source, right, where they have to fail the tri-state, state in order to pass this test. So with our laptop example, every time a laptop connects to a Type-C power brick, he will go through this sequence where he flips one last time and then fails, right? He needs to get back to that RD advertisement. What does it look like to succeed? So there's a specific test which really verifies the tri-source device will properly connect to another tri-sync. Just highlighting the main differences here. When the DUT goes to that tri-source state, the tester will flip to unattached sync. So the tester toggles like a DRP. He immediately detects source RP and would move through to that logical attach wait. And then finally, after CCD bounce, the tester goes attached sync, just like a real DRP would. And so the point here is tri-source should end up as the initial source every time he runs into a pure DRP. The most common issue we tend to see with this tri-source stuff is that tri-source getting back to that tri-source state in time. He's allowed a max of CCD bounce plus tDetach, so 200 plus 20 or 220 milliseconds. And we have seen DUTs that violate this check, like you see here in this example. This is what it looks like in the power tracker. Okay, so there is some alt mode testing in Type-C, and of course PD compliance also includes some alt mode testing, you probably know. Of course, if you have a DisplayPort device, there's a bunch of tests you have to pass at the VESA group to get their compliance logo. But each spec is kind of looking at different things. So in our test, the TD495, we focus on the source side. Could be a laptop that supports alternate modes. And we want to verify that they implement all the required behaviors. Starts the same as all the other tests, right? The CVS is in disabled. The source is actually a DRP, so he's toggling. Then the tester starts the connection sequence by showing RD on CC1 and RA on CC2. The DUT will continue toggling until he sees that RD from the tester. it should show RP, and then after CC debounce, the tester transitions from attached wait to the attached sync state. The DUT also waits CC debounce and then also goes attached source. He's still showing RP, right, as a source should. They're now in that connected state. Now, if the DUT supports PD, the two sides would negotiate an initial contract. We don't want to see any structured VDM messages until that initial contract is complete. So that's a clause that's called out in the test. After that, the tester will now start to respond to those vendor messages where the DUT is trying to discover if we support any alternate modes. The tester is supposed to respond that he does support alt mode 1. Now in this test, it's not required that the DUT sends the enter mode command. It's possible that he only works with some proprietary alt mode devices, and we can't really emulate all the different alt mode stuff out there. So if it does send the enter mode, we will ACK it, but that's pretty much all that's required. Okay, we make sure if the PUT is a receptacle that it sources VCONN. In the power tracker window at the bottom, you can see that we're showing voltage on CC1. Okay, we've seen that. I've hidden the CC2 voltage in a lot of these screenshots, though. If I enable that, we can see that VCONN is getting sourced at 5 volts. We go to disabled, and we need to see VCONN turn off right there. And that's what it looks like when VCONN turns off in the power tracker. After that, the tester transitions to disabled. We should see the DUT stop sourcing VCONN again and go back to that unattached state. There's a similar test for alt mode devices that operate as a sync. Okay, so here the DUT will be showing RD, sitting in unattached. Then the tester turns on. He's showing RP, so the PUT immediately goes to attach wait sync. The tester also transitions to attach wait source after CC debounce. Both sides go to attached at that stage. If the DUT supports PD, we'll set up an initial contract and then start the alt mode entry timer. So for devices that support USB, we're going to enumerate the device. Actually, we're going to keep the link up by sending get descriptors every 50 milliseconds, so that's what you see here. This is USB 2, but this is also repeated for USB 3 devices. Now normally this is where the source would initiate alt mode, but instead we're going to intentionally not issue any of those discovery commands and wait for the alt mode timer to expire. This is where we check the billboard descriptor. Okay, so this was put in to the USB spec specifically to alert higher layers that something went wrong with alt mode entry. So we check the billboard. It needs to be exposed between 1 second and 1.5 seconds. So we're forcing an error condition, right? And as long as we get that billboard, that clause is met. We then drop and reconnect. We repeat the test to make sure it can successfully get into that alt mode. We do a PD contract. Then we do discovery. We send discover SVids to see if it supports any of the special alt modes. We have to send another command to actually discover what alt mode it supports, and then we issue the enter alt mode. We need to see an ACK to this command, so we do check that. But that's it. We go to disabled. After that, on the tester, the DUT should float back to RD, although technically it has until TV bus off, which is 650 milliseconds to get back to that unattached sync state. So that's really generous, but we do check it, and that's it, right? We actually don't really verify that it actually enters any of these alt modes or any of the alt mode functionality. Okay, last test. We talked about VCONN already. We're going to look at this one specific test that's designed to test VCONN. There are 2 stages to the test. First stage, the tester as the source requests a swap. Then the tester, as the VCONN sync, will request a swap back. So we use this approach because there's really no repeatable way to get the DUT to initiate a swap. How do you get the DUT to do a VCONN swap unless you initiate it? Another important side note here, both of these commands are allowed, but these swap modes are also considered optional. So the DUT has to support what they call swap to on and swap to off in their VIF. And so that's only checked if they support those modes. It's pretty straightforward though. The DUT here is a DRP, okay, but he comes up as a source because the tester is showing RD. Notice the cable messages. Throughout most of these Type C tests, I didn't mention this, but we emulate an E-marked cable by showing RA on CC2. So the DUT is supposed to send cable messages to discover capabilities anytime he sees a marked cable. That's normal. The two sides negotiate an explicit contract. We can see the DUT sends a data role swap, but it's fine for the tester to reject that. Then we send the first VCONN swap. Okay, he's currently syncing VCONN. It's accepted. There's a PS ready sent once we're ready to source VCONN back to the DUT, so we do that. And that's the point where we need to check that the DUT stops sourcing VCONN on his side. Almost immediately, the tester issues another VCONN swap to go back to the sync role, which is also accepted. And in the power tracker, we can see that VCONN is going off here and back on at this stage right here. So that happens after that swap. That second swap is complete. Okay, that's the last test we're going to walk through. It was really more of a sprint, but I appreciate you guys hanging in there. I would like to thank my supporting cast, that is the Voyager M310C Analyzer Exerciser System, which made all of these test cases possible. We continue to expand the support for all the different compliance testing that's out there because, well, for one thing, it really showcases the flexibility that we have built into the tester. And we provide all the source code, too, for these compliance packages. So you can look at the test scripts and see exactly what they're doing during these tests. Okay, I know I've gone a little bit long here. I would love to handle any questions that I can. Let's see if we've got any questions. And of course we need to have our giveaway, and so that is also on deck. Let's see, someone writes, do DRPs have to support PD? So good question. They actually do not. As far as I know, that DRPs do not have to support PD. Most of them do, though, as I mentioned. Let's see, any other questions here? Told we have selected a winner from all the attendees. Bert Siminovich, congratulations. You have won the Mercury T2C Analyzer. Appreciate you hanging in there. Okay, so again, there's a USB workshop next week. Hopefully we'll see some of you at the workshop, and I look forward to doing more of these webinars in the future. Again, please look for the handouts coming by email with the link to the video, and that should be in the next day or two.